I will just cut out my video so it doesn't crash down. Okay, let's go. Good afternoon, everybody, and thank you, everyone, for inviting me to give this presentation. Today, I would like to discuss about the diversity in continent ocean transitions, and I will discuss potential implications for breakup style. So, rifted margins tend to be classified either as magma poor or magma rich based on a number of morphological features. And associated to this terminology, we make strong assumptions on the parameters controlling the formation and the tectonomagmatic interactions at breakup. Magma poor rifted margins are those where exhumed mantle is inferred in the continent ocean transition, supposedly related to have suppressed decompression melting at breakup. On the other side of the spectrum, we've got magma-rich rifted margins and the occurrence of seaward dipping reflections that we've seen just before, and they are interpreted as related to excess decompression melting at breakup. So today I would like to go beyond these magmatic archetypes and in a way that we have in mind and the related assumption we've got to discuss where, when, and how much magma forms during continental breakup, and what does the diversity in continent ocean transition tell us on the mode of continental breakup. So the aim of this presentation is first to present an interpretational approach to identify the relative timing between the amount of crustal thinning and onset of magmatic processes. And eventually, I would like to open the discussion on the relation between continent ocean structure and continental breakup style. So to do so, I will first focus on two case studies characterized by different tectonic and magmatic contexts. And first, Southeast India is characterized by a polyphase rifting between India and Antarctica, which occurred at the beginning of early Cretaceous and evolved into breakup in ancient time. On the other hand, we've got the Uruguay rifted margin, which was characterized by an onset of rifting that occurred in the latest Jurassic and was related to the formation here of rift basins that occur now obliquely to the final rift margin structure. And final rifting and breakup of the margin here coincides with the emplacement of the Parana Etandeka large igneous provinces. On these two examples, I will try to apply the same seismic interpretation approach to describe and characterize the first order of crustal architecture and the magmatic budget of their continent ocean transition. So let's just focus now on the Southeast Indian morphology. To do so, I just simply highlighted the interpretation here of the top basement in brown and the seismic interpretation of the moho, where I could identify it here in green. And some of the main rift structure and rift basin we can see. If we just now zoom in and try to look for evidence for magmatic products, we can tentatively interpret volcanic edifice here, sitting on top of an exhumed basement here, and associated with intrusives potentially within the basement and seals in the sediments, overlying sediments. Magmatic production appears much more clearly oceanward here, with potential volcanic edifice here and intrusives here at depth. If we just go to Uruguay now, so the section is located here, crosses the Punta del Este basin, which is observed here. And let's just have a look at the morphology of the margin. I simply again highlighted the top basement morphology here in brown, and below here in green, the moho. And some of the rift basin we could identify as the main rift structures. If we just now zoom in to look again for evidence of magmatic products, we can tentatively interpret volcanic edifices and intrusive within here on top of the rift basin here. But we can also clearly identify some nice SDR seaward dipping reflections on top of which we can see here a continentward onlap of the post-rift sediments. So the objective here now is to characterize the relative timing between the amount of crystal thinning and magmatic processes. So to do so, I will first identify crystal margin domains, which will illustrate the amount of crystal thinning. So first here, you see you've got the proximal domain in both margin, where you see that moho and sub-basement are parallel, and you see very little crystal thinning. If we go further oceanward, what we see is that the sub-basement is deepening and the moho is shallowing, eventually tapering out to leading place to exhumed mantle in the case of India, or here just leaving a piece of thin continental crust. If we go on the other side, what we see is again a tabular crust with sub-basement and moho that are parallel in both cases, and the crust is between 5 to 8 kilometers thick. And in between, we've got this piece of crust that is thicker than the adjacent oceanic domain, and with nature is uncertain, corresponding to the continent-ocean transition. So here, in this continent-ocean transition, in between what we can interpret as continent and as ocean, the volume of intrusive magmatism and the nature of the basement itself are difficult to constrain based on seismic observations only. And several interpretations appear plausible, which would involve variable magmatic volumes. If we propose different interpretations for the nature of the basement, what are the implications for continental breakup style? So now I will just take you through different extreme interpretations of the continent-ocean transition, and I will try to discuss the interpretation for magmatic production at breakup. So highlighted here in blue, what you see is a reference to the magmatic production of standard seafloor spreading, so roughly 7 kilometers thick, plus or minus 1 kilometer. Here in gray would be the apparent crystal thickness between the interpreted top basement and moho here in green. And here in green is the inferred thickness of serpentinized mantle here, or in brown corresponds to the remnants of continental crust that we can interpret in the continent-ocean transition. And eventually, what you've got here in red is the implication of this interpretation for the magmatic budget of the CUT. And what you can see here is in the first scenario where we suggest that most of the continent-ocean transition is made of magmatic crust. Well, in this case, we've got the magmatic production that exceeds seafloor spreading standard in both cases, whether we consider the Southeast Indian magma pore margin or the Uruguayan one. On the other side, what we can suggest is that in the second scenario, is that part of this basement still contains remnants of serpentinized mantle or continental crust. In that case, this drastically reduces the amount of the melt production, which appears much more progressive compared to the other scenario. So those two scenarios lead to drastically different tectonomagmatic interactions at breakup, involving either a nexus production of magmatism or a progressive emplacement of magmatism. This, which can be interpreted of different, to have different implications for the mode of breakup, whether corresponding to something that will be quite fast. That's why I call it instantaneous at geological timescale. Whereas on the other hand, we will have something which will be much more gradual and progressive. Now I would like to take you through some potential case studies which could illustrate this breakup style. And so I will come back, but based from former work on the Southeast Indian, on the Southeast Greenland margin. And I just show some previous work which has been done on this margin, which should suggest that here we have a very a narrow continent-ocean transition related to the emplacement of high fast melting rates. And here, this has been validated by drilling results. Continent-ward, there is indeed a component of continent which is below the seaward dipping reflection, but oceanward, it seems to be that below these reflections, the crust appears to be entirely magmatic. So in that case, we could even come back to define this continent-ocean boundary, having something quite sharp, a narrow continent-ocean transition. And now we just try to take you through another example, an example of gradual breakup. And for this, I would like to take you to the Antarctica rifted margin, and with a line located here. And here, what we see is that the margin is related to a progressive increase in melt production and is related to the emplacement of a wide continent-ocean transition. And here, what we see is that from the continent to the ocean, we see an evolution of the structural style with an oceanward deepening of the fault routing level. Here, toward the continent, the fault are routing at a shallow level, whereas oceanward, they are routing much deeper and on an interface which will become oceanward, the moho of the oceanic crust. So this change in the deepening of fault routing level is related to a change in the nature, is also related to a change in its nature. And continent-ward, what we observe is probably a strong effect of hydration processes, and notably of serpentinization of the exhumed mantle, which control basement rheology and the structural style. Whereas when we go oceanward, the progressive importance of melt production is related to much more interaction between serpentinization, hydration processes, and magmatic processes. And the magmatic production will be much more important, controlling the structural style oceanward and eventually controlling the emplacement of the oceanic crust and breakup. So to sum up and to conclude, we've got here different style. What I try to show is that we can have different style of breakup, which imply different melt production. And that the diversity in continent-ocean transitions reflects different interplays of processes at breakup in the different rifted margins. Of course, magmatic production is a key player, but what is also interesting to look at to understand the spectrum of rifted margin and continent-ocean transition is the relative timing of magmatic processes relative to the amount of crustal thinning. So this is what is expressed here. In the Antarctica rifted margin, we thin the crust to completely. We even exhumed mantle before the magmatic processes became really important and evolved and led to breakup. Whereas on the other side, with the Uruguayan rifted margin, we only slightly thinned the crust before the magmatic processes became important and led to breakup. So here in this presentation, what I tried to present you was a bit conceptual, and I would like to stress out that this came out from the fact that the amount of melt produced during breakup is quite difficult to evaluate from seismic observations only, and we lack drilling constraints from many rifted margins to really validate some of the models we proposed. And I think there is an added value to further develop combined observational and quantitative approaches to investigate rifted margin and to go further into the discussion of breakup processes. So thank you. And if you have any questions.
Thank you very much. We already have a lot of questions for you. And the first one was Robert Winch.
Okay. We'll try to see them.
Robert, do you ask the question yourself, please?
My question was, in Eastern India, you showed a cross-section that seemed to imply a normal fault between the Indian crust and its underlying mantle. And did I interpret that cross-section properly? Maybe here, yes. Is the crust mantle wedge on the left side of the upper figure? It's in green as the mantle crust boundary. Is it also a fault, a normal fault?
I'm not sure I understood all the details of your question, but if I just zoom into there, I guess you're asking about this interpretation here?
Yes.
Okay. In the end, what in brown, I highlighted what I call the continent at top of basement, but in fact, there are two top basements here, potentially. So here, and again, it's seismic interpretation, so I do not pretend I have the solution. There are potentially different solutions. What I try to do is what was fitting structurally what I was observing. So I'm not saying there is one unique solution, but what I suggested is indeed that there was here some sort of a fault that was exhuming and associated here to other oceanward faults. And to me, the end of the continental crust was terminating somewhere here. And here it would be some sort of on top, this layer here likely corresponds to likely includes also some synkinematic sediments and intruded in volcanoclastic sediments. So again, this is an interpretation. So.
Okay, thank you.
Next, we had one comment from Antonio. I'll leave that as a comment, and then Gary Kana had a question.
You want me to go now, or?
Yep, please go ahead.
Julie, so I had some questions from the Antarctic and Australian margins.
Oh, Gary.
I always find it interesting that basically the bathymetry of the so-called COT, let's go, yes, yeah, let me see, I've got a pointer here somewhere. I should have been more organized. No tools for me today. All right, that right there where you go from the blue to the green, it always surprises me that the bathymetry is rather similar, the relief, the general relief, telling me that basically the crustal thickness in Antarctica, but particularly here in Antarctica, that shows that that's serpentinized pretites as opposed to more typical ocean crust.
How should I, in a way, when I, how should I answer this? I agree with you, Gary. This is just to say that in a way, when I call continent ocean transition, if in a way for me it's an uncertainty zone. So from where it's dark blue means I'm quite confident this is oceanic. Where it's where it's gray, I'm confident it's continental, and in between, in a way, it becomes very difficult to say whether we are fully oceanic or not. So possibly the true boundary could be further continentward, where you've got a significant change in the structural style between this area and this one. I'm open to this. This is based on the work of Morgan Gillard, and I didn't change it because I didn't work as well as her on the section. So, but from the bathymetry, from the evolution of bathymetry, there is a clear difference between this side and this one. That's.
Thank you.